Okay, so we're off and running. And today we're going to talk about another way to integrate. So we introduced the antiderivatives or the indefinite integrals, and basically we used the rules that we knew backwards and we outlined them. So if you go back to this, we've got the basic formulas and properties, and based on those 5 things, we're able to do about all of our examples. So we're going to get a little more sophisticated with it today. If y'all remember when we learned the chain rule for taking derivatives, we took the outer derivative times the inner derivative. So you may or may not notice it, but what we're going to learn today is basically reversing the concept of the chain rule through substitution. Okay, so what we want to do to begin with is understand differential notation and using that method to do our differentiation. So if I've got, all this is saying is if I have y equals f of x, oops, wrong side, get a little thicker. And I want to take this, technically this is not really the way, if I were to tell you in great detail, remember the dy dx is a synonym for f prime of x, right? Well, in essence, if we think about, algebra, we can multiply both sides by the denominator. And if we did that here, we would end up with dy equals f prime of x times dx. It's not really technically the way to think of it, but it's probably a good kind of analogy. So in essence, we can say basically if I've got, we don't have to mess with this intermediate thinking. We can just say if y equals f of x, then dy equals f prime of x times dx. So we're just going to start doing this for today's purposes. So let's practice that a little bit. So if I'm finding dy for y equals x cubed, and dy equals 3x squared dx. If I've got u equals, and they're going to call it, in function notation, they're calling this h of x, but we're going to say u equals ln of 2 plus x squared. Then du equals 1 over 2 plus x squared times 2x. Okay, so that's the chain rule. And then times dx. So that was our f prime of x dx. Looks better if I say du equals 2x over 2 plus x squared dx. Let's do one more. Let's say that v is defined as e to the negative 5t. Okay, so the variable of integration is always on the right-hand side of this. So we're going to say dv equals e to the negative 5t, and then by the chain rule, that's the outer derivative. Now multiply by negative 5. and then the dt we have to tack on at the end for this differential. So cleaning that up, dv equals negative 5e to the negative 5t dt. Okay, so that's the differential notation that we're going to need in order to do substitution effectively. So let's look at our first example. Now, you can read this procedure, but I think the best way to learn it is just through example. So I'm going to create a starter sample. Okay, so I'm going to create a starter sample here. So essentially what this is saying is figure out something that looks like it makes a good substitution. And typically, if it's like multiple polynomials, you want to pick the higher degree expression. So, and if you get it wrong, you'll start to get tangled up in something that doesn't work out, so you back up and try something new. But good percentage of the time you can figure it out on the first guess. So since the expression x squared minus 3x plus 7 is higher degree than 2x minus 3, I want to try that first. So I'm going to say let u, and the way they say it up here is select substitution that appears to simplify the integrand. Try u, so du is a factor of the integrand. Well, that's kind of hard to discover what they mean without trying an example. So essentially, take the more complicated part of the expression and try it first. So u equals x squared minus 3x plus 7. Okay, so once we got u figured out, we're going to go back and do this thing here. So I'm going to take the differential and say, then du is equal to 2x minus 3 dx. Okay, so why is this helpful? Well, look at this. This is exactly what du is. So since du equals 2x minus 3 quantity times dx, I can substitute that part of the, or that factor in the integrand with du. Now this other thing we already declared to be u. So everything now in my integral is in terms of u. So what we're really looking at is u to the 4th du. And if that was x to the 4th dx, we know exactly what to do, so we know what to do, just now it's called u instead. So using the basic rule, this is u to the 4 plus 1 divided by 4 plus 1 plus my constant of integration. So it's u to the 5th over 5 plus c. And now the only thing we have to do now is replace u. And u is x squared minus 3x plus 7. So our answer is x squared minus 3x plus 7 to the 5th over 5, or I'm going to put it out here as times 1/5, so that's the over 5, plus the constant of integration. Okay, so by creating and substituting u for some block in the integrand that looks like it would be the easiest to whittle down, we can come up with a way to substitute and then integrate something much simpler and then substitute back the original declaration there. So, okay, so that's the idea, and that's what this is saying here if you ferret those steps out. All right, so let's move on to some more examples. So this A part is very much like the one we just did. So I want you guys to take a minute and try that out. And be great if I hear back from you with an answer for A. It's very much like the one we just did, and then we'll do B. But let me give you a couple minutes to see what you come up with for A.
I got 1/7 times 3x plus 4 to the 7th power plus c.
Okay, that would be correct. And anybody need to see that one worked out, or should we move on to B? Okay, so if nobody speaks up, I'll just go ahead and get started on B here. So you would have let U be 3x plus 4, and would have looked a lot like that one from the last page. So let's move on to B. And here, we know that integrating e to the x is very easy because we know that that turns out to be e to the x, just like, well, plus c, e to the x plus c. And the derivative of e to the x plus c is e to the x. So let's set u equal to what the exponent here is. That's kind of, we'll try that, you know. If it works, it works. That kind of looks good because we know that when I take du, I get 2t dt, and lo and behold, that's what we have here. So we're going to let u equal t squared, then du equals 2t dt. Okay, and then when we reinspect this, we see that this is du. And since u is t squared, I'll rewrite this as e to the u. So now in terms of u only, we have the integral of e to the u du, just because magically du turned out to be this portion of the integrand. So this equals e to the u plus some constant, and back substituting the u, this is e to the t squared plus some constant. Okay, so sometimes things work out quite nicely right from the get-go. Not only that, if you're uncertain if you got it right, you can always check yourself. Just take the derivative of solution Okay, if we take the derivative of the solution, you should get back the integrand. So let's take the derivative of our answer, e to the t squared plus c prime. Okay, so here I'll have to use the chain rule. Outer e to the t squared is e to the t squared, and then inside I've got to take t squared, and that becomes 2t. And then any constant is 0. And this matches the integrand. Okay, so just like you can check subtraction with addition, you can check integration with differentiation. Okay, so let's do some more that are just increase the complexity a little bit. So for part A, we want an integral of 1 over 4x plus 7 dx. So your instincts might tell you to use, you don't have a lot of choices here. So we'll do 4x plus 7 for u. And let's get du real quick. Du would be equal to 4 dx. So we can write this as the integral of 1 over u. And I don't want dx in there, I need du. But dx needs to be solved for, so I can substitute. We didn't match it up exactly when we took du like we did in the last one, but it's not hard to fix that. If I divide both sides by 4, then I can see that du over 4, oops, equals dx. So for dx, I can put du over 4. Okay, so let's just bring that constant 1 over 4 out front and make this 1 over u du. Okay, we saw in our last page here, or our last section, that 1 over x is ln of the absolute value of x plus c. So I'll take this to be 1/4 times ln of the absolute value of u plus my constant. And when I do my final substitution back in, I get 1/4 ln of the absolute value of our declared u. Okay, so that wasn't too bad either. Let's move on to B. Okay, let me ask for a suggestion here instead of just throwing one out there for you. What would you try first here for you? Anybody? Okay. Well, we're gonna go ahead and take this blob that is the exponent for e, because we know how to do e to the something. So let's go ahead and we'll simplify life by making it the negative at the same time. So let's try u to the negative t squared, and obviously that's a higher degree than just the t. So when I take du, I'm going to get negative 2t dt. Okay. So if you identify it directly, that's fine. If you want to solve for dt first so it's more obvious to you, then all we would have to do is divide both sides by negative 2t. And we would get dt equals negative du over 2t. Okay, that way I know exactly what to put in here for dt. So let's do that. We're going to get t e to the u times negative du over 2t. Okay, and it looks like there's still a t in there muddying things up. We need it to be all in terms of u du, but we have a t in the denominator in this factor, and we have a t in the numerator, and they cancel each other out. So there is no longer a t, and I have the integral, and I'm going to put the negative 1/2 out here. That's my negative 1/2, and all I have left in here is the eu to the u du. Okay, so now we know what to do. It's negative 1/2 e to the u plus c. So all I have to do is back substitute our u part in, and we get negative 1/2 e to the negative t squared plus c. All right, I didn't do a great job of leaving room for part C, but let's see if I can squeeze it in. Okay, so we've got this. I know that when I take the derivative of an x cubed, I'm going to get a 3x squared, and then that's going to match this x squared, so that's going to take care of this factor. So let's go ahead and let u equal x cubed plus 5. Then du equals 3x squared, and then the constant is 0, so 3x squared dx. Okay, so dx itself is going to equal du over 3x squared. So we have an integral of 4x squared times the square root of u, and then dx we're going to call du over 3x squared. So the x squareds cancel or divide out, and the 4 over 3 remains. So I'll put that out here as 4/3. And then the square root of u, let's think of it as u to the 1/2 for simplicity. Okay, so my integral of 4 is 4/3 constant times u to the 1/2 plus 1 over 1/2 plus 1 plus c. Okay, so that equals 4/3 u to the 3/2 over 3/2 plus c. So that's 4/3. I'm going to flip that and multiply, so that becomes times 2/3 u to the 3/2 plus c. So we have 8/9 u to the 3/2 plus c. Now let's get u back in the game. So that's 8/9 x cubed plus 5 to the 3/2 plus c. Okay, so that's the idea of integration by substitution. Show you one more little trick that's a slight variation on these. Let me add a page. And let's say that I wanted to find the integral of x over square root of x plus 2 dx. Okay, this is interesting because when I let u equal something, I don't change the, I'm not going to, when I take the derivative, I'm not going to jump down by a degree and match anything. But let's try what we think would work and see what happens. Well, it turns out to be not so bad, since we know that, right? If I say that u equals x plus 2, then here's an x. What is it in terms of u? Well, then in terms of u, x would be u minus 2. So then we can think of that as the integral of u minus 2 for x over the square root of u, and then du equals 1 dx. So I get to do a direct substitution. Du and dx are equivalent because when I kind of jumped to solving for x before I even bothered taking the differential here that we usually need. But that just turns out to be a 1-for-1 there. So we just say du. So now all I'm going to do is do what we are allowed to, split that up into 2 and integrate minus okay, so everything I've tapped into is back on this section. I just split this out into, I broke it out into 2 common denominator fractions. And so u over u to the 1/2 is equal to u to the 1/2. Okay, so this would become and we'll think of that as u to the negative 1/2. Okay, so this is just algebra. So this is u to the 1/2 plus 2/2 over 3/2 minus 2 okay, so we just got some cleaning up to do. So this would be, come way over here, flipping that, we're going to get 2/3 u to the 3/2 minus 2, and since I'm going to flip that half, that becomes 2 times 2, so minus 4 u to the 1/2 plus c. And finally getting our u back in there, it's 2/3 x plus 2 for u to the 3/2 minus 4 x plus 2 for u to the 1/2 plus c. Okay. All right, so that's our integration by substitution, and we got a little bit of time left. If you haven't, this is like the exact opposite of my last class, where all of a sudden it was over and I didn't feel like I did anything, and now like I've done what I expected to do, and we've got some time left. So we can either, you guys can drop out and get an early start, or if you got some questions,